Fortunately, Adrian's saved me from having to do a 40-minute presentation on stuff, because he's just taken 15 minutes of some of the things we're going to cover just briefly, which is fantastic. So we're going to talk about bushfire, smoke, energy and hospitals, or let's just convert that to we all love clean air, right? But what is clean air? Well, if I said to you, let's improve our air quality and let's reduce energy doing it, what would you say? Would you say that maybe there's some sort of magic in having to do that? Well, we thought, let's give this a go. Let's have a bit of a trial and see what happens. So it's important that if you're going to have a crazy idea that you be nuts with mates. And so I think Adrian mentioned before, we call air handling units things. Well, the project that we've got together with Race 2030 and the Victorian Building Authority, the University of South Australia and Plasma Shield and us, came up with a project that involves the retrofitting of an advanced multimodal air treatment system in a healthcare facility, an IHEA, and we're going to monitor the energy consumption and the indoor air quality, and we're going to do it over 9 months. And so we've started this. There are heaps of aspects that are being measured that we'll have a look at shortly, but for us today, we're just going to have a look at the indoor air quality results just as a snapshot, hot off the press. Now, as Adrian said before, we all know that you check your filter performance, don't you? Everyone nod? Yep. Of course we do, yep. So what we're going to do is just take a little bit of a step back, and if you have a look at the top of the slides here, you'll see that on every slide in the slide pack, there's just this little reminder here of what we're talking about. So let's talk about air and the air in this room. And so the air in this room has stuff in it. And if we wanted to look at it in its varying degrees and where it exists, then the 10 micron stuff would be the size, the equivalent size of a 4-storey building. The 2.5 micron stuff would be about the size of 1 floor. The 1 micron stuff would be about the size of a large fridge. And everyone just heard Adrian say F8 or F9, and F8 sits around about that large fridge. So what we're doing in health is, if we've got F9s, which are a MERV 16 equivalent, that's sort of the size of stuff that we're filtering out of our air. So of all the components that are in there, we're getting down to the large fridge size, and that's our standard. But what about all of the tiny grains of sugar that are also floating around? And what sort of percentage of those things, and what are they? And for years, we've just said the fridge will be okay. But we can actually get down to sizes of cans of Coke and cans of and grains of sugar in terms of what we're going to filter. So here's a typical F9 filter, and just a little bit of a refresh. So this EPM1 is the reference for the 1 micron, and this filter should be about 83% efficient for stuff that's fridge size trying to go through it, okay? If you start looking at the 2.5 or the 10, it'll catch 95% of the 4-storey buildings that are trying to go through it, okay? But what's it going to catch that's smaller? Well, let's see. So if we compare a HEPA filter and an F9, we know that F9s have a lower pressure drop and they have a lower cost. And so this is sort of where we've stuck for many years, or slightly below, just due to cost and availability and technology. But what if something was available that allowed us to take the next step? And take the next step to perform or even outperform HEPA. So this is a typical airborne indoor pollutant table, and it shows you a whole range of things. And remember, we sort of set our standards now, all of us, to the left of that red line. So we sort of do nothing about most viruses, outdoor sprays, carbon particles, wood smoke. We sort of can't, because our holes in our filters only stop the fridges, and this stuff's a lot smaller. So what we did with our project is we have two wards that have very similar air handling units, almost identical. And so what we did is we said, let's use one and study it, and let's make some changes to another one and study it. And so what we decided we would do was do this trial where we put this bioHEPA in and see what happens. Bearing in mind that everyone knows we still have to have our dilution rate, so 2 to 6. So we've still got to have coming into here, we've still got to have 2 lots of something, and that something's got all that other stuff in it that we just talked about. So what if conceptually we could go from having dilution where we dilute and we set our air efficiency based on the fact that energy emissions and costs, we do the best we can. We can't tip infection control out of balance, but we have to appreciate that this side of the puzzle is a heavy weighing component. But what if we could actually get ourselves to a decontamination point where we can do the same things, but we can remove odour, destroy mould, and keep our infection control, and maybe do it a little bit better than we currently do. So let's take out our traditional filters and heat wheels and see what happens. So here's the heat wheel that used to exist at that location in the air handling unit, and you can see there that it's a fairly big unit. And there's the filters that we looked at before, and that photograph on the right is of that filter when it was removed. So it was incredibly clean. It was in a really good condition, and it was 2.5 years old. So we're pretty lucky. We've maintained our place pretty well. And in its place, we installed this product here. And if you go out and have a look at the standard plasma shield, you'll be able to see one of those smaller units. The geometry for us luckily fitted really well with our unit. And so in terms of the location in the air handling unit, it fitted pretty well. So remember, here's our control unit, and we're having a look at some data in a minute of that unit, and we're going to compare it to this one, which is our new one. And all we've done is we've pulled the blue squares out on the left hand and just put our bioHEPA in on the right, keeping in mind that what we call a fine filter is actually only catching fridges. So let's see what we catch going forward. So that's the physical location of where it was, and we just basically pulled that out and installed that. Looks good, doesn't it, when you just go from A to B like that in a slide? We all know that's how stuff works in engineering. And so that was installed, and then we commenced doing some data and working out what it looked like. So the key metrics that were being assessed were particle number concentrations, which we're focusing on today, ultra-fine particles, so stuff smaller than the fridges that we normally just don't care about because we don't know what to do with them, and those other things that are on there, ozone, VOCs, and they're all part of the study going onwards, and that data will be published once the study's finished. So let's have a little bit of a look at air quality, because stuff happens with air, doesn't it? So this is Mildura. Could you push play, please? Imagine if this was your house. There we go. Get the dog inside. Uh-oh. Okay. And so that's, now that size particle, that can actually be caught by our current filtering, can't it? Because that's lots of fridges floating through the air, all right? Fridges and bigger stuff. But for us, if we had that happen, we'd have to probably change these filters pretty shortly after. And what I want you to picture in your mind soon is what you just saw you could see. What if you couldn't see the stuff that's floating around, but it looks like that if you were small enough to see it? So here we've got our average particles that were going through the studied air handling unit, so the one without any changes. And you can see that the average filter penetration rate for the particles 0.3 to 25 microns, so left of the red box at the top. remembering our efficiency should be for this filter somewhere around 83%. And amazingly, we had about 13.6 penetration. So this filter is performing almost exactly as designed in situ in our facility, which is pretty amazing because you put filters in and you just sort of expect they work. But this actually allowed us to understand that we were right on the money. So then what happened is we had a look at the intervention unit. And you can see that for the intervention unit, we had 0.004% of penetration of the same size particles through the intervention unit. And so whatever it's filtering, it's doing it well. Whatever that stuff is, we don't yet know, but we know it's there. And it's currently getting into our wards through that unit, but it ain't getting into our wards through this unit. And so if we're supplying cleaner air, whatever that cleaner means, we've improved something, and the study will resolve just how good that is and whether that actually relates to a real factor in a room. So if we just have a look at this, this is an indication of the total number of particles that are in the air, in the supply air chamber. And you can see that the particles in that range that are bigger than fridges, typically on a typical day, you know, we might be around 1.5 million. On a bad day, we might have 4 million particles per cubic metre of air. Everyone got that? The intervention unit, there's nothing getting through, okay? But these are the sorts of things that are being presented to your filters every day of the week, all day. So just remember that figure, you know, let's pick sort of 2 million as a number, all right? 2 million of something floating around per cubic metre of air. Now, if you look at the ultra-fine stuff, which is we're now starting to get down into our Coke cans and our grains of sugar. Our filter penetration rate on our intervention unit is at 0.64%, and our penetration rate of our existing system, without doing anything, is only 8%, which is still pretty damn good without doing anything. So. But you can see in terms of metrics that is about a 12 times reduction on what we were putting into our space. Now this was all carried out through the non-bushfire period. And then the bushfire period started and a serendipitous natural experiment occurred, and we just want to make sure there's a disclaimer here. We didn't start the fire, but we did have one. And what we know is that if you test this stuff with controlled burns, that you get these sorts of things occurring. But when you have a bushfire, you also lose houses, cars, and other things. And these other nasties are also present and floating around. So Echuca is located here. And on the 11th of January this year, we had a fire start at a little place called IHEA, which is there. And I took a photo. I was at that fire. And it's a pretty clear photo because where it was taken from, which was about, that's probably 100 metres from the fire, maybe a bit closer. You can see we're in clear air, aren't we? But how far can you see into that? And what's the quality of the air doing there? Well, let's have a look. So a pretty ordinary day. Lots of airborne particulates, not stuff we're going to catch with our filters, because all of this stuff, this is way down around that Coke can size or smaller. And we got some data on this. Now remember, what was the number I asked you to remember before about what a typical day looks like? what do we get? About a couple of million, thank you. A couple of million things floating around in our air per cubic metre. Well, on this particular day, this is a couple of days later because smoke takes a while to travel, unless the fire's at your doorstep. So on this particular day, about 170 million particles per cubic metre. That's a fair lot whacking away at your filters, isn't it? And a 30-time increase on the average particle number concentration that we would have on a normal day. The line here, that's the intervention unit. So that's what we were getting coming out of our intervention unit. Anyone see what the number to the left of that would be? Almost zero. So this is a graph of the finer particles. So now we're looking at the Coke cans down to the grains of sugar. And our normal unit was passing 13 million. It was doing the best it could, but 13 million's stuff got through it, and only 12,000 stuff got through the intervention unit. Hallelujah, 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 hallelujah. All right, so you were here, you heard it first. Something happened today. We don't know what happened, but we just found something, didn't we? And we can do something different to what we've always done. We don't know what we've found, and we don't know the total number of particles and what they contain, but we know there's a lot of Coke cans and small pieces of sugar floating around. They're here right now in this room. It's just that we can't see them because our eyes are bigger than the 4-storey buildings. So on the preceding days after the fires, we had 3 or 4 days there, and you can see that there was consistent days where we had 100 million particles per cubic metre of air in that normal range of your 0.3 to 25 micron range, and you can see that the intervention unit had pretty much nothing going through it. Now, was this a surprise? Well, sort of, but sort of not. When you test something in a small area, you can't just extrapolate that and say that'll work if you multiply it 50,000 times bigger on a big air handling unit. But what we do know is that if you test a purifier with HEPA, activated carbon and UV, and you challenge it with some of these nasties that come out of fires, that's about the best sort of performance you get out of it. The testing in the lab of the unit we've got came up with that, and now we've got some real world data that sort of supports it. Now, what that means to human health, what that means to future healthcare and indoor air quality, I'll leave to others to decide. But what we do know is that we've got some compelling data that something's better than it used to be. We're also probably the only BMS people to, like our BMS, we can log on and we can see particles in our airway. So this is the new normal, folks, that you should be able to do if you are interested and want to do it. You can just, we talk about pressure. Years ago, pressure was something someone had to go and hook up and look at a big magnehelic. Now we see it online. So this sort of technology is available, and we integrated it to our BMS so we could see it, because if you can't measure it, you can't manage it. So in conclusion, bushfire incidents can degrade your air quality. Highly polluted outside air can exist for long periods of time, particularly in our areas. Toxic gases and vapours that can attach to particles can then be inhaled and released into lung tissue. And we know that metabolic process works and is one of the factors associated with cigarette smoking. Particle count measurements provide really sensitive measures of smoke, but it doesn't tell us what's in there, and so maybe some work to be done in that space. But what we do know is that we've had some really great results, and the filtration unit that we've got in addresses the smoke risk, which is great for us in our area. efficiently removes particles, and also VOC, SVOC, mould and other things are really promising, and more to come. Thank you.